Hi, in this video, we are going to talk about teleportation. Teleportation is a very interesting protocol. Last time we had talked about super dense coding, and we saw that we could not transmit 2 bits of classical information using one quantum channel or 1 bit or 1 qubit. Now, let me ask the reverse question. Can you transmit 1 qubit worth of information if you had access to 2 classical channels? So suppose you have 2 classical channels given by these 2 double wires, right? And you're able to transmit zeros and ones, classical zeros and ones. Can you transmit a quantum state psi is equal to alpha 0 plus beta 1? If you think about this a little bit, the answer is no. Now, just like in the super dense coding protocol, let's add a single shared entangled state, right? So we have a shared entangled state, and then is it possible to, so 1 e-bit. So the question is, so we have 2 bits and one shared entangled state, right? Is this now a possibility to transmit a quantum state? And this is where the teleportation protocol comes to play. So let's say we have a black box and we have a state psi to be transmitted. So let's say a black box. And somehow over some long distance, the state magically appears over here. Now, we know that the no cloning theorem, right? You have, suppose you have this unitary, and we saw that in the no cloning theorem, you cannot build a circuit for an unknown state psi like this. So this circuit is not possible, right? So is it possible to build such a black box to sort of teleport or transmit the state psi? Indeed, the teleportation protocol does something like this. However, this state, the original state, gets destroyed and the teleported state appears on the other side. So that is the teleportation protocol. Now let's go a little bit deeper in this protocol. So let's look at the circuits that one can build to make such a thing happen. So we have Alice and Bob. So Alice, this Alice part, and this is the state psi. Let me call this psi is equal to alpha ket 0 plus beta ket 1. This is the state to be transmitted or teleported. And then we have this shared entanglement. So this is um, the maximally entangled state 0, 0 plus 1, 1 over square root of 2. And I'm going to draw this dashed line to distinguish between Bob's side and Alice side and Bob's side, right? So this is the top 2 qubits are Alice's qubits. Psi is the state to be transmitted. And qubit 2 and qubit 3, these 2 qubits are, one is for Alice and the last one is for Bob, and they share an entangled state. And we have, one quantum state to be transmitted, but we also can transmit 2 bits of classical information. So let's draw this circuit. So let me first draw the circuit. There is a C0 gate that gets applied. So there is a C0 gate, and then followed by a Hadamard gate over here. Okay, so Alice applies the C0 gate with the control on the first qubit and the target on the second. followed by Hadamard gate. Then Alice measures her qubits, and the measured states are sent over a classical channel to Bob. Okay, now Bob receives these qubits, classical bits, and applies certain gates to it. I will not draw them right now, but let's say he applies certain gates to it depending on the classical bit. So this is the classical bit 1. So let me call that M1. This is classical bit 2. This is M2. And there are some gates. Let me call that U1 and U2. And let's see if we can recover the state psi over here. Okay. So let's analyze this circuit. So we have, I'm going to draw these vertical red lines. It's a timeline. So as time progresses, we will see what state appears over here. So this is psi 0. The initial state, psi 0, is, of course, alpha 0 plus beta 1, which is get psi in the first qubit, and then tensored with 0, 0 plus 1, 1 over square root of 2. These are the shared entangled state. In fact, I can write this psi 0 as alpha 0 tensor gets 0, 0 plus 1, 1 over square root of 2 plus beta ket 1 tensor 0, 0 plus 1, 1 over square root of 2. So this is our initial state. Then the C0 gate gets applied between the first two qubits. So let me, after the C0 gate gets applied, let me call this state psi 1. So what will psi 1 be? So psi 1 will be, so this first part will not get affected because the control bit is 0. So it will not change the second bit. So I'll write it as it is. This is the control bit. Since it is 0, the second qubit doesn't get affected. On the other hand, in the second part, the control bit is 1. So the next bit gets affected. It will change from a 0 to 1 or 1 to 0, right? So this will be the psi 1. And then a Hadamard gate gets applied next. So this is at the end of the Hadamard gate being applied, this will be, I'll call this psi 2. Okay, so what will psi 2 be? Psi 2 will be Hadamard applying on the first bit. So this will be 0 plus 1 over square root of 2 tensor 0, 0 plus 1, 1 over square root of 2 plus beta into 0 minus 1 over square root of 2 and tensor with this state, which is 1, 0 plus 0, 1 over square root of 2. And I can rewrite this state as by taking out, by using the distributive property of the tensor product. And since we are going to measure the first two qubits, so after this, the Hadamard gets applied, we are going to do these measurements over here, right? So let's rewrite this state a little bit. So I can rewrite this state. So rearranging the terms. terms, what do we get? We can write psi 2 as half 0, 0 tensor alpha 0 plus beta 1. Okay, so I'm writing in such a way that so these two bits are going to be measured. So I'm going to write it by taking the first two bits and then writing the first two bit as a tensor product of the third bit, right? So this will be plus 0, 1 tensor alpha 1 plus beta 0. And you can just do the algebra. It's quite simple over here. And then plus half 1, 0 tensor alpha 0 plus, minus beta 1. And finally, 1, 1 will be alpha 1 minus beta 0. All right. So I have written this state in such a way. So if I measure the first two qubits, I'll get answer 0, 0 with probability 1 over 2 square. Answer 0, 1 with again probability 1 over 2 square, that is 1 over 4. And so on, right? And the state of the third qubit are post measurement. If a 0, 0 will be obtained, then it will be in this state. If a 0, 1 will be obtained, it will be in this state. If a 1, 0 will be obtained, it will be in this state. And finally, if a 1, 1 will be obtained, it will be in this state. Right? So you will see that whatever measurement we get, the third qubit is in some sort of variant, small deviation from the original state. Right? So, and that gives an idea what gates which Bob should apply. So this third qubit is Bob's qubit, right? So now the third, we'll be able to figure out from this what U1 and U2 are. And if I look at these states, you will see that the gates U1 and U2, I can now erase this and write this as x to the power m2 and z to the power m1, where x and z are the polygates. So indeed, if 0, 0 is obtained, then Bob doesn't have to do anything, right? Because the state is already psi at Bob's end. If 0, 1 is obtained, then Bob has to apply an X gate, right? So if 0, 1 is obtained, then first qubit is 0 and this is 1. So Bob will only have to apply x to the power 1, right? So it will be the X gate. Similarly, if 1, 0 is obtained, Bob will have to apply a Z gate. And finally, if 1, 1 is obtained, Bob will have to apply a X gate followed by a Z gate. And then Bob indeed can recover the state psi at his end. However, notice that the state psi is already measured and is collapsed. So it will collapse to either a classical 0 or 1. So this does not violate the no cloning theorem. And in terms of the resource theory, one can say that if I have one E bit, which is one entangled state, plus two classical bits, then these are more resourceful, or I can say that I can transmit at least 1 qubit using that. And that's the teleportation protocol. This is the teleportation circuit.